Hi, welcome back to a new lecture from Transformers for Vision series. In today's lecture, we will be once again diving into multi-head attention. In the last lecture, we learned about how we can implement MHA or multi-head attention in a naive way by simply looping through different attention heads and concatenating context vector matrices to produce the final context vector matrix. So this part we looked at in the last lecture. In today's lecture, we will see how to implement multi-head attention in a much more efficient way so that large language models can experience scalability using the technique called weight splits. So today's lecture is going to be a lot of focus on dimensionality. There is batches. There are number of tokens. Each token has a dimension. Then there are attention heads in multi-head attention, and each attention head has a dimensionality. So bunch of numbers you will be going to see in today's lecture. So please pay good attention. At the end of the lecture, you will have a fairly good mathematical picture and a fairly good understanding about how multi-head attention is actually implemented in practice in large language models. So one point that I want to mention before we proceed ahead is that this is the last lecture on attention mechanism in this series. So by the end of today's lecture, you should feel very comfortable to think about the transformer block, to think about the attention mechanism, to think about context vectors, and also to implement them in a simple Python code. So let's first do a brief recap of what we looked at in the last lecture. What was multi-head attention? So in multi-head attention, we will have more than one query matrix, key matrix, and value matrix. So this figure was summing up our whole idea, which we discussed in the previous lecture very nicely. So let's say your inputs is a bunch of vectors of, say, dimension 3. So your input vectors are 3-dimensional. So these input vectors we need to convert into query key value space. But how do we convert this into query key value space? Using query weight matrix, key weight matrix, and value weight matrix. So this is the weight matrix for query. This is the weight matrix for key, and this is the weight matrix for value. In the absence of multi-head attention, or if the multi-head attention just had one head, you will only have one weight matrix. But here you can see that there are two weight matrices, WQ1 and WQ2, which will operate separately on the input to convert them into Q1, which is first set of queries, Q2, which is the second set of queries. So now in the query space, because this attention head has two heads, this multi-head attention has two heads, you have two query vectors corresponding to every single input vector. Same thing applies for keys and values. So this is the most simplified form of multi-head attention with two attention heads. Now, because you have two attention heads, you will have two matrices corresponding to your attention scores. So how did you get the first attention? How did you get the first query matrix Q1? Q1 was the product of your input X and WQ1. So X multiplied by WQ1 will give you Q1. X multiplied by WQ2 will give you Q2. So this is matrix multiplication. Now, what if X is a 6x3 matrix? What does this mean? There are 6 tokens and each token has 3 dimensions. And let's say the query key value space has a dimensionality of 2, which means here the dimensionality of a single token is 2. So I should have 6 tokens and each token should have 2 dimensions. Here also I should have 6 tokens. Each token should have 2 dimensions, correct? Same thing applies for value and keys also. So how do you convert a 6x3 matrix into a 6x2 matrix? You simply multiply with a 3x2 matrix. So your WQ1 will be a 3x2 matrix. Your WQ2 will be also a 3x2 matrix. So this 3x2 matrix will convert your 6x3 matrix, which are 6 tokens with each of them being 3-dimensional. It will be converted into 6 tokens with each of them being 2-dimensional. And like that, you will have 2 attention heads. And because of that, you will have 2 queries corresponding to every single input token. Now, to calculate attention scores, usually what you do is you take the dot product between query and key. So Q dot key transpose or Q multiplied by key transpose. So here you have now two attention score matrices, not just one, each of dimension what? It'll be, I mean, although I have drawn it as 3 by 3 here, if we have 6 tokens, we should have an attention score matrix of dimension 6 by 6. And like that, we should have two attention score matrices. The first matrix will be the result of dot product between Q1 and K1. So this is Q1 dot K1 transpose. I'm not sure how much you can see the transpose T. It's a little bit blurred. The second one is Q2 dot K2 transpose. So this first matrix will be the attention scores between queries and keys in the head number 1. The second matrix, which is behind, will be the attention scores between queries and keys in head number 2. Now, attention scores are converted to attention weights by first you doing scaling, then you perform masking. So scaling is division by 1 by square root of dimensionality of the key space. Let me just reduce the thickness of the pen. So scaling is done by dividing by square root of dk, where dk is the dimensionality of the key space. In our case, the dimensionality of the key space is 2. Masking is done by putting minus infinity. So this will be minus infinite. This will be minus infinite. This will be minus infinite. So that when you take softmax, all the upper triangular elements will become zeros. So softmax of minus infinity in a series will be 0 because softmax is e raised to x, e raised to zi divided by sigma e raised to zi. So if zi is minus infinite, e raised to minus infinite will be 0. So all these items will become 0 after taking softmax. And then you apply dropout. So here now you convert attention scores into attention weights because every row will sum up to 1. So this will be 1. This might be like 0.8, 0.2. It's not 3 by 3, by the way. We are considering 6 tokens, but if our input had only 3 tokens, this would have been perfect. So if this, instead of this being 6, if it was just 3 tokens, each being dimension 3, then this 3 by 3 representation is perfect because you have 3 keys and 3 queries. And similarly, the last row will also sum up to be 1. So these are attention weights. Now you apply dropout mask with a certain probability. So if probability P is equal to 0.5, randomly you will be masking half of the elements from your attention weights matrix. And the remaining elements, which are not masked, will be scaled up by a factor of 1 by 1 minus P. This also we discussed in the last lecture. The reason why this scaling is done is because if we don't do the scaling now, you are expecting similar magnitude output with on an average half the number of values or half the number of parameters, which is not possible because you're on an average reducing the number of available parameters by half, which means the remaining half of the parameters should do the similar job. So that the values of those weights should be scaled up proportionate to the probability with which you are performing masking. Now, after you perform dropout, you have now your final masked attention weights with dropout. And then you are ready to calculate the context vectors. How do you get context vectors? This attention weights after dropping out, you multiply with values. So value is again, you have two you have two heads, head 1 and head 2. So you have two value matrices. After dropout also, you have two matrices. So those are attention weights after dropout. You had two attention weight matrices. Then you drop out in each of them separately. So you have two dropout matrices. The matrix number 1 is this. Matrix number 2 is the one behind. And then correspondingly here in values, you have V1, which is the first value matrix. This is V2, which is the second value matrix. So if you have 3 input tokens with each of them being 3-dimensional, here you will have 3 tokens, each of them being 2-dimensional. Here also you will have 3 tokens, each of them being 2-dimensional. Now, when you multiply the attention weights after dropout with values, you will get context vectors Z. So what is the dimensionality here, by the way? This should be 3 by 3 because we just initially we also started with 6 by 3. We later changed it to 3 by 3 just for the purpose of illustration. So 3 tokens, each of them being 3-dimensional, which means your attention weight should also be 3 by 3. Now you have this one being 3 by 3. This is also 3 by 3. And 3 by 2, you will multiply with 3 by 3 to get 3 by 2, right? So 3 by 3 matrix multiplied by 3 by 2 matrix will result in 3 by 2 matrix. Now, what is the 3 by 2 matrix? Those are these. So you will have 3 context vectors in each attention heads of dimensionality 2. So in the first attention head, let me just erase this once. This is the attention head number 1. This is the attention head number 2. You will have how many context vectors in attention head 1? You will have 3 context vectors in attention head 1. Why? Because you had 3 input vectors. So you will have 3 context vectors in attention head 1. And the dimensionality, we have defined the dimensionality here manually. We can define it to be whatever, but the dimensionality of your vectors in the query key value space is 2, which means your context vectors which result from the operation of query key and value will also be 2. And like that, you have 3 vectors in attention head number 1. Like that, you also have 3 vectors in attention head number 2. And then what you do is, so these are now 2 context vector matrices, and but you just need 1 context vector matrix with just 3 rows. So then what you do is you concatenate this 2-dimensional vector from the attention head 1 and the corresponding 2-dimensional context vector from attention head 2 to produce a 4-dimensional context vector 1, 2, 3, 4. And how many such 4-dimensional context vectors will be there after this combination? There will be 3. So 3 because in the input you have 3 input vectors. Each of them was of 3 dimension. By the time you reach the context vector matrix, you have 3 vectors, but each of them are of 4 dimensions. Here you had 3 vectors, each of them 2 dimension. Here you had 3 vectors, each of them 2 dimension. Then you concatenate them along the row to get 3 vectors, each of them of 4 dimensions. So this is how, using multi-head attention, we went from inputs of dimensionality 3 to outputs of dimensionality 4. Now the dimensionality will of course depend on what is our D out or dimensionality of the output, right? So it's something that we define. So this is what we discussed. So if we had 6 input vectors, each of 3 dimensions, in each attention head, you will have 6 vectors, and the dimensionality in each individual head will be 2 if it's a multi-head attention with 2 heads. And then the final one will have 4 dimensions. Final vectors, context vectors will have 4 dimensions. Let's try to put some numbers. We already did this exercise in the last lecture, but it'll be great to do once more. So let's say number of tokens, num tokens equal to 6, and let's say dimensions at the input equal to 3, and dimension at the output is equal to 6, and number of attention heads is equal to 3. Now, given these things, what will be the dimensionality in each attention head? Dimensionality in each attention head will be whatever is the output dimension. So here output dimension is 6, that divided by number of heads. So that will be 6 divided by 3 equal to 2. So each attention head should have a dimensionality of 2, correct? Now, when we concatenate, how many attention heads are we concatenating? We are concatenating 3 such attention heads. So each attention head, inside each attention head, your query vector will be number of tokens, 6 multiplied by dimensionality inside each head, which is 2. Key vector will be 6 by 2. Value vector will be value matrix, key matrix, and query matrix will be 6 by 2. What about WQ, WK, and WV? So you are converting something of 6 by 3 to 6 by 2. So this should be 3 by 2. This should be 3 by 2. This should be 3 by 2. Then your attention weights should be a matrix of size 6 by 6 because you have 6 queries and 6 keys. So after dropout also it will be 6 by 6. But like that, how many weight matrices you will have? You will have 3 weight matrices because you have 3 attention heads. Number of heads is 3. And finally, when you are concatenating or just before concatenating, your context vector matrices before concat. What will be the dimensionality of this? There should be 6 context vectors, each with dimensionality equal to 2. And after concatenation, it will become 6 by, there are 3 heads, each of them having a dimensionality 2. So 2 plus 2 plus 2, that will be 6. So after concatenation, this will become 6. So your input was 6 by 3. You had 6 tokens, each with dimensionality 3. But your output, you were expecting to have 6 by 6 because you have 6 tokens, and D out you are defining to be 6. And here you can see that your D out is 6, number of tokens is 6. So this is what we do in the simplest implementation of multi-head attention. All right. So I hope this recap gives you a fairly good idea about what we covered in the last lecture. Now, this naive implementation of multi-head attention has a problem. Here is the problem. Let's say I have 3 attention heads, right? My Q1 will be what? My Q1 will be X multiplied by WQ1. Q2 will be X multiplied by WQ2. These are matrix multiplications. Q3 will be X multiplied by WQ3. This is how I get query matrix in attention head number 1, number 2, and number 3. The problem here is, in GPT-2 small version, they had 12 attention heads. In GPT-3, they had 96 attention heads. So now imagine I have to perform this calculation 96 times to calculate my query vector in each of the 96 attention heads. It's very inefficient. It's not very scalable because we'll have to do this using for loop. So looping is not a very efficient operation, unlike matrix multiplication. The simplest example to understand this is considering matrix multiplication itself. So let's say A equal to 1, 2, 3, 4, B equal to 5, 6, 7, 8. And let's say I want to do matrix multiplication. The naive way to do this is for I equal to 1 to 2, for J equal to 1 to 2. We can also define a K if we want, for K equal to 1 to 2. And then we say, let's say result is stored in something like C. Then C of JK is equal to A of IJ multiplied by B of JK, something like this. I'm not paying full attention to whether this I, JK should be, which one should be in the outer loop and which one should be in the inner loop. But basically what we have to do in the naive way of implementation of matrix multiplication is this row should get multiplied by this column. Then that row should get multiplied by this column. Then this row should get multiplied by this column. And then this same row should get multiplied by this column. Now imagine your matrix is very big. This calculation will take forever. And instead of this, there is a better way to do the same matrix multiplication in Python, which is C equal to A multiplied by B. So this symbol performs the matrix multiplication in a much more efficient way in Python. So it can be done in a tensorial way rather than using for loops. So this is where we should be heading. So how can we perform the same multi-head attention mechanism without having to do these many matrix multiplications? How can we reduce the number of matrix multiplications? That's our question. So we don't want to be doing 96 matrix multiplications for finding each query in each attention head. If we were using GPT-3, we don't want to be doing 12 matrix multiplication for finding each query if we were using, let's say, GPT-2 small. So what we could do instead, what if we did something like this? So currently what we are doing is, attention, without a T is missing here. You have inputs X, okay? Then X will get multiplied by WQ1 to get Q1. X will get multiplied by WQ2 to get Q2. So the D out is 2 here. Q1 has dimensionality equal to 2. Here maybe D in can be 2 or whatever. It can be 2, it can be 3. So if this is 2, this will be a 2 by 2 matrix. And here each query will be of D out equal to 2. Here also D out equal to 2. But instead of having these two weight matrices for query, because here we had two weight matrices, because here we are saying there are two attention heads. If we had 96 attention heads, we would have gone from WQ1 all the way till WQ96. But instead of that, let's say we just have one weight matrix for query and one for key and one for value. But the dimensionality of this is such that whatever is the final dimensionality, so let's say final dimensionality in our actual query space should be, let's say it is 2. And let's say we have 2 attention heads, then the dimensionality over here should be 2 multiplied by 2 equal to 4. On the other hand, if we had if we were supposed to have 3 attention heads, and if we want the final dimensionality, or if we want the dimensionality of the actual query, key, and value vectors to be 2, and if we had 3 attention heads in the multi-head attention, then here D out would have been 6. But what we are saying here is, we won't be performing X multiplied by WQ1, X multiplied by WQ2, that we won't be doing, but rather we'll be simply performing X multiplied by WQ is equal to some query matrix. And this query matrix, we can now split manually into Q1 and Q2. So that way we accomplish what we wanted to, because we want Q1 and K1 to calculate attention scores in the attention head number 1, because Q1 multiplied by K1 transpose is the attention scores in attention head number 1. So of course we want attention scores in different heads to be calculated. We want attention weights in different heads to be calculated. But before all of that, we want Q, we want K, and we want values. So here the number of matrix multiplications that that ended up producing Q1 and Q2 was 2 matrix multiplications, X with WQ1 and X with WQ2. On the other hand, here the number of matrix multiplications that we did was just 1. We just multiplied X with WQ to produce like a parent query matrix, which we can split into Q1 and Q2 and say that Q1 belongs to head number 1, Q2 belongs to head number 2. I will show you why this is so effective. One reason why you can already imagine why this is so effective is because now, even if you had 96 attention heads, the number of matrix multiplications will still be just 1. Then you can split it into Q1, Q2, etc. up to Q96. So this is what we are trying to now see. How can we implement something called as weight splitting to perform the implementation of multi-head attention instead of performing multiple matrix multiplications in for loop, right? So this is what we are trying to see today. In the last lecture, we had a basic implementation of multi-head attention using classes. So we had these tokens, dream, big, and work for it. And then we defined this causal attention class where we were initializing the weight matrices for query, key, and value. We defined dropout, and we defined the output dimension, which was being passed into this into the function. And then we said key equal to W multiplied by input, or input multiplied by W, query equal to input multiplied by key, W key. Sorry, query equal to W input multiplied by W query, values equal to input X multiplied by W value. Attention scores was the dot product between query and key. Attention score after masking will be negative infinity in the upper triangle. Attention weights will be attention scores divided by square root of D, that is this. And then you take softmax. So this we have already covered in the last lecture. And the resultant thing was something that looked like this. We had a context vector whose dimension was depending on the number of tokens and the output dimension, correct? So now let's just quickly run the code. I'm pretty sure this is fairly straightforward because we have already covered this in the last lecture. But what we are going to do is, let's just go through this. So torch.manual.seed of 123 means you are defining the seed for your random number generator. Then context length equal to bash.shape of 1. But there is one line where we are defining the bash. So yeah, so here we are saying bash equal to torch.stack of inputs comma inputs. So basically this is just to create batch size of 2. What if I just wanted batch size to be 1? So you see here, so this is batch size, the 1 is batch size, 6 is what? 6 is number of input tokens per batch, 3 is the number of dimensions per token. So I can concatenate 2 of these inputs together to produce batch size of 2. It's the simplest way, otherwise I'll have to define some other inputs. But here you can play with the batch size like this, okay? But let's keep the batch size 2 for now. Now, if the batch size is 2, and if the number of tokens per batch is 6, and if the dimensionality of each token is 3, okay? And now these are my inputs. These 6 vectors in 3 dimensions, they are my inputs. What we do is, and then we say the input dimensionality is nothing but the last dimension of my inputs matrix. The last dimension of the input matrix is number of columns. Number of columns is 3. So D in should be 3. And D out, we say it should be 2. So the final context vector that comes out of my multi-head attention should be 2-dimensional. So if I have batch size of 2, 6 input vectors, each of 3 dimensions, my final output should be batch size of 2, 6 context vectors with dimensionality 2 each. That is what I'm expecting finally. Okay. So let me run this code. Then what we did was we defined this class called multi-head attention wrapper, which was a wrapper around the causal attention. And here we were doing a for loop. Can you point out the part where we are doing the for loop for each attention head separately? This is the part where we are doing the for loop. So for dash in range of number of heads, it's basically you are looping through head number 1, head number 2, etc. So here the number of heads that we have defined is in the input. Where is that? So here number of heads is equal to 4. So this for loop will operate 4 times, each time calculating the context vectors at the output of each head. And then once you have all the calculation for all the 4 heads done, you have to perform concatenation along the row. So this is that concatenation function, torch.cat. Okay. So our context length was the number of tokens, which was 6. So context length equal to bash.shape of 1. So we can say it would be batch.shape of 1, or we can say inputs.shape of 0, basically number of rows. That should also be fine. Then D in comma D out is 3 comma 2. Then multi-head attention. This is the object which is created out of this class multi-head attention wrapper. Into this wrapper, we are passing input dimension, output dimension should be 2, input dimension should be 3. I can just write this here, but I think writing like this is cleaner. Context length is 6. 0.0 is dropout, so I'm not asking any dropout to be done. So dropout is happening at a probability of 0. Number of attention heads equal to 4. And then let me run this. So now the object is defined. And then to this object, I pass my batch. Which one is my batch? My batch is this guy. The batch with 2 items, each item being 6 token and each token being 3 dimension. And then I can print the context vector and context vector dimension. So now you see, because we had 2 batches, okay, because we had 2 batches, we should have 6 plus 6, 12 vectors, 6 vectors corresponding to first batch, 6 vectors corresponding to second batch. Where do we see that? So these are the 6 vectors. So each row is 1 vector. And these 6 vectors correspond to batch 1. These 6 vectors are corresponding to batch 2. Now, what is the dimensionality of my context vector after concatenation? Before concatenation, the dimensionality of each of my context vector was 2. After concatenation, it will become 8 because I have 8 attention heads. Sorry, I have 4 attention heads. Each attention head is taking care of dimensionality 2. So here the first two columns will correspond to the first attention head, second two columns, the third and fourth columns corresponding to attention head 2. These the 1, 2, 3, 4, 5, 6, fifth and sixth column correspond to next attention head, and then these two columns correspond to last attention head. So if the attention heads, this was 2, then my output dimensionality would have been 4-dimensional. Each context vector would have been of dimensionality 4. And let me actually not print the context vector. If I don't print the context vector, here you can see the dimensionality of the query key value space is 2. Number of attention heads is 2, which means my output context vector dimension should be 2 times 2, which is 4. Is it 4? Yes, it is 4. The number of tokens in each batch is 6, which means the middle item should be 6. Fine. Batch size is 2, which means this should be 2. Correct. Now, what if I keep my batch size equal to 1? So now batch size will be 1. Now this became 164. So this is what we implemented in the last lecture. In today's lecture, we will see how we can play with this dimensionality to implement the idea of the weight split. So I am implementing these weight splits in 11 steps, but I'm not going to read these steps right now. Let's dive deeper into each of these steps, and then we'll come back to these 11 steps to make sure that it makes sense to us, right? And then we will look at the code. So let's see what we should do first. Let me zoom in a little bit. First is, let's start with the input. So let's say I have 3 input tokens. So here I'm simplifying a few things. So let's say I have 3 input tokens. The kid smiles. So this is the token corresponding to kid. The kid smiles. So here, what is the dimensionality of each token? It is 6-dimensional. Dimension 1, 2, 3, 4, 5, 6. Okay. So we have 3 tokens, each token being 6-dimensional, and our batch size is 1. So that is why our dimensionality at the start will be 1, 3, 6. 1 is the batch size, 3 is the number of tokens per batch, 6 is the dimensionality. Now, one more thing you can notice is the brackets over here. So you are having 6 dimensions per token. So the first set of bracket, the innermost pair of bracket will be corresponding to, it will envelop your 6 dimensions. The pair of brackets just outside, which is this opening bracket and this closing bracket, will correspond to the fact that you have 3 tokens of each 6 dimensions. So if you did not have the last bracket, this opening bracket and this closing bracket, then you would not have 3 dimensions. You would only have 2 dimensions in your tensor, because you only have one more layer of brackets, opening and closing brackets outside. But you have another layer of opening and closing bracket, which is this one and this one, which says you now have batch dimension also. So what if we had a batch size of 2 instead of 1? How will this look like? It will look something like this. So let me delete this. If my batch size was 2, I will have to replicate what? Should I copy with this bracket or without this bracket? So batch is whatever is there in my outermost bracket. So I have to copy everything that is there in my outermost bracket, put a comma, and then paste it here. Now this is of batch size 2. So the dimensionality of this will be 2, 3, 6, correct? What if I did something like this? Let me go back. What if I copy pasted something like this? Then this would have been of dimensionality 1 by 4 by 6, because you have now 4 vectors, each of dimension 6, but you have 1 batch. All right, so this is how you can make sense of these, these tensors. Now we have to decide what should be our final output dimension and what should be our number of heads. Let's say our final output dimension should match the input dimension, which means when we create the final concatenated output vector, I don't want my dimensionality to change. So the dimensionality, let's keep it at 6. So output dimension will also be 6 for every single vector. And we'll say number of attention heads in the multi-head attention is 2. Fine. So we decided that. Next is we have to initialize WQ, WK, and WV. So by the way, WQ, WK, WV, let's see what should be the dimensions of each of these. So the dimensionality of WQ, WK, and WV are D in by D out. Where D in is equal to 6 and D out is equal to 6. So each of them will be 6 by 6. Now we can initialize, for the purpose of this demonstration, we can initialize these weight matrices as random matrices. And then we can calculate query, key, and value. So query is nothing but X multiplied by WQ. Key is X multiplied by WK. Value is X multiplied by WV. Now let's look at one of these because the dimensionality is the same across query, key, and value. So we just need to look at one of this to understand the dimensions. So the dimension of X, which is input, is 1 by 3 by 6. 1 is the batch size. 3 is the number of tokens. 6 is the dimensionality of each token. WQ is 6 by 6. So result of 1 by 3 by 6 multiplied by 6 by 6 will be 1 by 3 by 6 again. Because if this was a matrix, just two matrices, ignore the batch dimension, you would be multiplying a 3 by 6 matrix with a 6 by 6 matrix to result in 3 by 6 matrix. You just have an extra batch dimension for your input. So 1 by 3 by 6 multiplied by 6 by 6 will result in 1 by 3 by 6. So we can actually implement this. I have written a code over here. So let's say these are my 3 input tokens, each of dimension 6. Okay. And then I can define a random matrices as weight, WQ, WK, and WV. And Q is equal to input X multiplied by WQ, K is equal to input X multiplied by WK, and then WV. And then if we run this, we can calculate the dimensionality of each of them. So dimensionality of Q should be 1 by 3 by 6. Dimensionality of K should be 1 by 3 by 6. Value should also be 1 by 3 by 6. Now let's just display query key value tensors, how they will look like. So now this is the query tensor, key tensor, and value tensor. Now can we see where is our token? So this is query corresponding to token number 1. This is query corresponding to token 2. And this is query corresponding to token 3. So the first pair of bracket here is for wrapping individual query vectors. Second pair of bracket here is for wrapping around these triplets, because your batch size, your context size is 3. You have 3 tokens per context window. And the last pair of brackets is to wrap your batch dimension. Like that, you have key and value. Now what we do is, we do something interesting. We unroll the last dimension of query key value to include number of heads, because so far we did not include number of heads anywhere. We want to explicitly include number of heads so that we can make it part of our matrix multiplication or tensor multiplication. So what we do is, our query key value is now 1 by 3 by 6, where 6 is the dimensionality at the input. Now this 6 is processed such that you have 2 attention heads, and each attention head looks at dimensionality 3 each, right? And then you concatenate to get back 6. That is how you do this. So this 6, actually we can say this 6 is coming because you have 2 attention heads and each attention head is taking care of 3 dimensions each. So this 6 we can write as 2 by 3. So now you are going from a 3D tensor. So this was a 3-dimensional tensor to a 4-dimensional tensor. Why do we have 4 dimensions? This is the first dimension, which is batch. Second dimension, which is number of tokens. Third dimension, which is number of heads. Fourth dimension is the dimensionality of the query key value space in each head of the multi-head attention. So what we have to do is we have to unroll the last dimension to 2 by 3. So 6 should become 2 by 3. So that can be very easily done in code. So yeah, this is just the weight matrices being printed. So the unrolling happens like this. So Q will become Q dot view of 1, 3, number of heads, head dimension. So originally it was 1, 3, 6. Now it will become 1, 3, number of heads is 2, 1, 3, 2, 3 instead of 1, 3, 6. So Q will become 1, 3, 2, 3. Same for key and same for value. And then when you display query key value after this unrolling, you will get something like this. I have copy pasted the same thing here in a little bit more easy to understand way. Let me first delete these annotations so that it will probably be easier for you to read. So this is now query after unrolling, key after unrolling, value after unrolling. Now let's see what each of these things are. We have two heads. So this is corresponding to head number 1. This is corresponding to head number 2. And we have totally how many input tokens? We had 3 input tokens going to both heads. So now this plus this is the token number 1. This is token number 2. And this is token number 3. This is head 1. This is head 2. This is head 1. This is head 2. So now you can see the brackets. The first bracket, innermost pair of brackets is enclosing the 3-dimensional query key value space vectors in each attention heads. Second pair of bracket is wrapping around your input vector in attention head number 1 and head number 2. Third bracket is wrapping around 1, 2, 3, all the 3 input vectors. Fourth bracket is wrapping around your batch dimension. So you will see 4 pairs of opening and closing brackets. 4 like starting from innermost to outermost brackets. So these brackets signify 4-dimensional tensor. Now, so far, so good. Okay, so let's take a step back. Let's see what all we have done so far. We defined input tokens. We had 3 tokens of each dimensionality 6. We said it also has a batch dimension, which will be 1 by 3 by 6. Then we said we want to convert this into Q, K, V using WQ, WK, and WV. And we said the output dimensionality finally should be same as input dimensionality, which is 6. So each of these were 6 by 6 matrices, which means my query will be now 1 by 3 by 6. Key by 3 by 6. Key will be 1 by 3 by 6. Value will also be 1 by 3 by 6. Then we said we will now unroll this. 1 by 3 by 6 should become 1 by 3 by 2 by 3, where 3 is the dimensionality in each attention head. 2 is the total number of attention heads. 3 is the total number of input tokens. 1 is the number of batch size. Okay. Now, if you notice, the grouping is happening based on tokens. So here, this grouping. So ignore the batch, ignore these two, ignore the batch, and ignore the number of tokens. But if you just look at within one token, we are grouping head number 1 and head number 2 into token number 1. Basically, if we draw this as a tree, the way this looks like is it will look like this. Head 1, head 2, and then this is token 1. Then you have token 2 and token 3. This is what we have. What would be more useful for us will be, instead of this kind of a tree, if we had it based on attention heads. So in head number 1, token 1 is being passed. In head number 1, token 2 is being passed. In head number 1, token 3 is also being passed. And then we have head 2. And same 3 tokens also go to head 2, right? So it will be nice if we had these tokens grouped based on heads rather than heads being grouped into tokens. So instead of this, if we had this, it would have been better. So how can we do that? It is very simple. We can simply swap the last 2 dimensions, meaning instead of grouping my matrices based on heads, or instead of in a simpler language, instead of keeping token as the parent node and heads as the children, I should have head 1. I should have all information about head 1 with me. Then I should have all information about head 2 with me. That way I can calculate attention scores corresponding to heads and then attention weights corresponding to heads, because that is what we want to do ultimately. So what we can do is, instead of saying batch, if the dimensionality is now 1, 3, 2, 3, which is batch, number of tokens, number of heads, dimensionality per head, instead of saying this, I can just say, earlier I said last 2 dimensions. I did not mean last 2 dimensions, these 2 dimensions. What I can say is swap these 2 dimensions. So number of heads should come here. Number of tokens should go here. Now, if we have a matrix of dimension 1 by 3, and if I want to make this 3 come here and 1 go here, this should become 3 by 1. What is this called? This is called as transpose. Here also we are doing transpose, but the dimensions along which we are doing transpose is dimension number 1 and 2. Why? Because this is dimension 0. In Python, the indexing starts with 0. This is dimension 1. This is dimension 2. And this is dimension 3. So now what we have to do is we have to take a transpose of query key and value such that dimension 1 and 2 are swapped. So this is the code using which you can do that. Basically, simply do q dot transpose of 1, 2, k dot transpose of 1, 2, value dot transpose of 1, 2. So the dimensions 1 and 2 will get exchanged. Now, once they get exchanged, just see how this looks like, how the query key value looks like. Numbers will not change. It's just that their orientation will change. Now, what is this? This is token number 1. This is token number 2. This is token number 3. This plus this will form head 1. These 3 will form attention head 2. Similarly, this will be attention head 2 in key, and these 3 will be attention head 1 in key. Similarly, this will be token 1, token 2, token 3. So this is basically the query key value representation of your input tokens. You had 3 input tokens, each of them were of 6 dimensions. But your output dimensionality should also remain same, but you have 2 attention heads in your multi-head attention, which means the dimensionality of each token inside query space, key space, and value space will be 6 by 2, which is equal to 3. And as you can see here, it is 3. This is dimension 1, dimension 2, and dimension 3. So each token in query key value space is represented by 3 dimensions, not 6 dimensions. Only after coming out of multi-head attention, it will get back to 6 dimensions. And now you are grouping based on head. So now you see the nodes is like you have attention head 1. So this is head 1. And head 1 is branching to token 1, token 2, token 3, and like that head 2 is also doing. So now we have information about head grouped into one single, opening and closing bracket. Okay, so this is much better than what we had just before. So let us just implement this in code. So in code, all we need to do is like take transpose, q dot transpose of 1 comma 2, key dot transpose of 1 comma 2, and value also. Then we get this grouping based on attention heads instead of grouping based on tokens. All right. Now let's go back. Now we are ready to calculate attention scores. So attention score is simply query dot key transpose. And where is this done? This usually we do in each attention head. So attention head 1 will have its own attention scores. Attention head 2 will have its own attention scores. Same for 3, right? If there are 3 attention heads, here there are only 2 attention heads. So if you look at this grouping, where is my attention head number 1 in query? These 3 belong to attention head number 1, right? In query. Similarly, these 3 are also attention head number 1 in key. So what I want to do is this, whatever is these 3, they should get multiplied with the transpose of these 3, correct? So what are these 3 numbers? Minus 9.02, minus 11 point this, minus 15.54. So this will remain as such, but then this will become transpose. This 3 by 3 sort of should become a transpose of itself. So now tell me, along which dimension should we take this transpose? So let's see what this transpose will look like. So my query is 1 by 2 by 3 by 3. What is that? 1 is the batch size. This is the number of attention heads. This is the number of tokens. And this is dimensionality in each attention head, right? Key, on the other hand, it should exchange a couple of things. One is number of tokens should go here, and head dimension should come here for key, not for query. Query can remain the same. We don't take the transpose of query, but we take the transpose of key. And why do we do this? Because first of all, we don't touch the batch. What if batch size was 1? What if the batch dimension did not exist at all? So anyway, we know that we don't take transpose. In the transpose, batch is not involved. Similarly, we also know that in the transpose, we are not mixing between attention head number 1 and head number 2. Because if we are doing q dot k transpose, it is between q of attention head 1 and k of attention head 2. So number of heads also, this dimension, head dimension also, we don't have to touch while taking the transpose. So that itself makes it clear that these are the 2 dimensions which I have to swap, or where I have to take the transpose to do key transpose, k dot t. And what are these dimensions? 0, 1, 2, 3. So basically you have to take key, you should transpose such that transpose happens along dimensions 2 and 3. So you can simply say k underscore t, which is the transpose of key, is k dot transpose of 2, 3. So that is also fairly easy. Just 1 line, 2 lines of implementation. Expected to be in range. Let me just run once the whole thing. Yeah. So now this is the transpose of key. So after we take the transpose, how will key look like? Key should look like as if this 3 by 3 matrix is transposed. So minus 6.2 should go here. 0.31 should go here. Similarly, this 14.11 should come here. Minus 5.03 should go here. Similarly, what else should happen? 1, 2, 3, 4. Okay, so here I can see an extra number. I think I might have copy pasted twice. Yeah, I can see one more thing copy pasted. This line is occurring 2 times. Let me just delete it. Yeah, and similarly, in key, you have 1 more attention head, 2 attention heads. So this minus 14.3 should go here. This minus 4.40 should go here. This diagonal should not change. Sorry, these 3 should not change. These diagonal elements should remain as such, but remaining should get swapped. Now let's see whether that is what is happening. So Q remains unchanged, but after transposing, if I delete all this annotations, you can see this 14.11 has reached here. This minus 5.03 has reached here. This minus 6.12 has come here. this 0.31 has come here, and diagonal elements should remain the same. 8.26. Here it is 8.26. Minus 0.16, minus 0.16, minus 1.45, minus 1.45. I mean, this is diagonal because there is a little bit of offset due to these extra brackets, but I hope you understand that these three are the diagonal elements. Same thing has happened for the head number 2. So now we successfully took a transpose of query. Okay, so just let us take a recap of what all did we do. We defined batch size 1. We had 3 tokens. Each tokens had a dimensionality of 6. Then we said we need WQ, WK, W value. So what we said was each of these should be 6 by 6 to result in query key value matrices QKV of 1 by 3 by 6. Then we said this 6 should be split into number of heads and dimensionality per head. So this became 1 by 3 by 2 by 3. Okay, so query was like this, key was like this. Then we said we had to take the transpose of key, correct? Or no. Just before that, we also had to do grouping based on heads rather than based on tokens. So what we first did was we swapped these two. We swapped these two such that it became 1 by 2 by 3 by 3. So this 3 was dimensionality of head. This 3 was number of tokens. This 2 was number of heads. This 1 is the batch size. So this was done for query key and value. Then we wanted to take query.key transpose. So before that, what we did was key, we took a transpose along the dimension number 2 and number 3. This is dimension 0, this is dimension 1, this is dimension 2 and dimension 3. So key dot transpose of dimension 2, 3. Key dot t of 2, 3. That is what we just did now. And then we can take the query dot key transpose. So now after transposing after transposing key, it would be like 1 by 2 by 3 by 3 only, but this 1 will be batch. So these two will remain the same. And we said batch and number of heads we don't have to touch because there could have been just no batching. There could have been just 1 head. But the last item will be number of tokens. Second last item will be dimensionality of each head. Okay. So I know that there are a lot of numbers going on here. The best way to understand this is just writing this yourself. You listen to the lecture and write it yourself. Otherwise, if you try to visualize, you will, of course, confuse between this 3 and this 3. It's very difficult to keep in your mind and keep track of this for the next few minutes, right? So the best thing is just write this on a handwritten note. Okay. Then the next step is finding attention score. Attention score is query multiplied by transpose of key. And then let's just see. So attention scores are query multiplied by transpose of key, and the attention score shape. This is an interesting thing. Attention score shape is 1, 2, 3, 3. Can you tell me how? 1 is batch size. 2 is number of attention heads. 3 is number of tokens. This 3 that is also number of tokens. Why? Because when you multiply Q with key transpose, your Q was batch size, batch, comma number of heads, comma number of tokens, comma head dimension, head dim. And key transpose was this came here, correct? Number of tokens at the end and head dimension here. So now the multiplication is happening between this matrix with this matrix. So resulting will be what? This by this. So now the result will be batch, comma heads, comma number of tokens, comma number of tokens. So the last 2 dimensions will be basically number of tokens. Number of tokens is 3, which is why this is 3 by 3. So now this is your attention scores matrix. Attention scores matrix is 1 by 2 by 3 by 3. And we can clearly see, so attention score will be calculated between every query and every key. Number of queries is equal to number of tokens. Number of keys is equal to number of tokens. So what was our query or our input? Our input was this sentence, the kid smiles. So we can write it like this. This is the query, this is the query kid. This is the query smiles. Similarly, this column is the key, this is the key kid. This is the key smiles. And these set of attention scores are from our head number 1. These scores are from head number 2. Okay, fairly straightforward. Now, what we have to do is, so far we did not touch any for loop. Nowhere for loop was involved. So what we are doing is very clean. Now we need to calculate attention weights. So what we first do is we apply the causal mask. So upper triangle elements will be negative infinity for both attention heads. So these both are at negative infinity. Then we do scaling. So scaling is 1 by square root of d. So I have written the code here. So first apply the mask. Then you get upper triangle to be minus infinity. Then the scaling is such that 1 by square root of dimensionality of each head. Dimensionality of each head is 3. So 1 by square root of 3. With that you divide and then you take softmax. So softmax is taken after dividing by square root of d to get attention weights. So now these are your attention weights after taking softmax. The upper triangle elements all will become 0 then. So let me show you the results here. These are the upper triangle elements which are supposed to be 0. Because if the query is it should not see the key kid and it should not see the key smiles, which means this should be 0, this should be 0. If query is kid, smiles is coming after kid. So it should not pay attention to the key smiles. So this should be 0. If query is smiles, it should pay attention to the kid and smiles. So the upper triangle, these 3 items should be 0. And you can see that those 3 are indeed 0 here. 0, 0, 0. This is also, these are also 0. And each individual row should sum up to 1. But attention weights never sum up to 1. See, this does not sum up to 1. This row does not sum up to 1. This row does not sum up to 1. However, attention weights sum up to 1. So this row sums up to 1. This row sums up to 1. The reason why this guy became 1 and this became 0 is because this value would have been so small compared to this value before taking softmax. And here it is also summing up to 1. Similarly, this row is 1. The sum of this row is also 1. Sum of this row is also 1. Fairly good. All right. And if you want to apply dropout, you can apply dropout with a certain probability. So here dropout is applied at a 10% probability if I'm not wrong. Yeah, dropout with a 10% probability, which means whichever elements are not dropped out will be scaled up by a factor of 1 by 1 minus p, which is equal to 1 by 1 minus 0.1, which is 1 by 0.9. And that is what? 1.11, right? Let me calculate. 1 by 0.9, 1.11. Yeah. So every number will be scaled, every remaining number will be scaled by this 1.11. So this 1 will become 1.11, whichever other surviving number. So 0.985 will become 0.985 multiplied by 1.11. Let's calculate that. 0.985 multiplied by 1.11111. This is 1.0944. It is indeed 1.0944. So this is how dropout works. So since the dropout probability is only 10%, maybe all elements are not getting dropped out. So here I don't see any of these major elements getting dropped out. Yeah, perhaps the dropped out item was this. In that case, it does not make any difference, right? So this is how you apply dropout to get the final attention weights after applying dropout. Now we are ready to calculate the context vector. So what is context vector usually? Context vector is attention weights multiplied by value, correct? Value matrix. What is attention weights here? attention weights was 1 by 2 by 3 by 3, correct? This is the batch size. This is the number of heads. This is the number of tokens. And this is the number of tokens. What about value? What is the dimensionality of value? It should be 1 by, so value we did last over here. We did not touch value after a point. So value after grouping by head was 1 by 2 by 3 by 3, I guess. So it was, yeah, I have literally written it here. So value was 1 by 2 by 3 by 3. Attention weights was 1 by 2 by 3 by 3. So here there was one difference. Although the dimensionality looks similar, they are not the same. So in attention weights, you had batch size. Batch size was 1. Number of attention heads, it is 2. Number of tokens, it is 3. Then this is also number of tokens. However, in value matrix, this is batch size 1. This is correct. Number of attention heads is 2. Correct. Number of tokens is 2. That is correct. But head dimension is the last one. That's also 3. That's also correct. So now if we multiply, for getting the context vector, if we multiply attention weights with value, what happens? So attention weights multiplied by value will be looking at matrix multiplication between these two and these two. And will that cause any problem? No, because you are multiplying a matrix of dimension number of tokens, comma, number of tokens, which is what? Which is 3, 3, with a matrix of size, number of tokens, comma, head dimension. Number of tokens, comma, head dim. So here, number of tokens was 3, head dim was 3 as well. So this would result in a matrix of dimension number of tokens, comma, head dim, which should be 3 by 3. So my final attention scores, my final context vectors should be 1 by 2 by 3 by 3. So 1 by 2 by 3 by 3. So this is number of tokens. This is a dimensionality in each attention head. This is batch size, and this is the number of heads. So 1 by 2 by 3 by 3. Let's see if that is the case. So yes, context vector shape is 1 by 2 by 3 by 3. And let's see. So the first 3 vectors are the 3 context vectors corresponding to my 3 input tokens in attention head number 1. The next 3 context vectors, which you can see here, are the context vectors corresponding to my 3 input tokens in attention head number 2. Now, we are pretty much ready. So far, no for loop was used, right? Everything happened through tensor operation. Now we just need to perform concatenation. And that's also basically reshaping. So all we need to do is, okay, first of all, by the way, how do we have to reshape? We have to reshape such that token number 1 over here and token number 1 will get concatenated along the row dimension, correct? So the last dimensionality is the number of dimensions, I guess, head dimension. So I have to convert this 3 and this 2 into just 6. So earlier we did a rollout. Now we have to pack it back again. So basically reformatting. So what I have written is, first, we have to swap the dimension number 1 and 2. Where is that 1 and 2? So the values we can swap is to bring the number of attention heads and the dimensionality per head close to each other. These two numbers we can swap, 2 and 3 we can swap, which is taking a transpose along dimension number 1 and dimension number 2. So that is what we are implementing here. Context vector, we are transposing along dimension 1 and dimension 2. If we do that, we get this kind of a matrix. So I'm just displaying that over here. Where is that? So this is after swapping. So now where are our three tokens? So this is token number 1. This is token 2. And this is token 3. We had 3 tokens. And now all we need to do is like concatenate this and this. Basically combine the last 2 dimensions to make it one 6-dimensional token instead of token 1 split into 2 3-dimensional tokens. So that we can very simply implement using the same similar technique, opposite technique what we did earlier. Earlier we did unpack it into 1, 3, 3, 2. Now we just need to pack it back into 1, 6, 3. So we can implement it over here. So we say reshape it such that first dimension is batch, second dimension is the sequence length, which is the context window or the number of tokens. Third dimension is basically the product of number of attention heads and head dimension, which is 6. So it won't be 1, 6, 3, it will be 1, 3, 6. So now the final result will be 1, 3, 6. And now what is this? This is the context vector corresponding to token number 1. This is the context vector corresponding to token number 2. And this is the third context vector corresponding to token number 3. So we originally started with 3 tokens, which was the kid smiles, right? Something like that. Yeah, the kid smiles. So now we have, instead of the input embeddings, we have now 3 context vectors, each corresponding to 1 token. So this is what the entire multi-head attention mechanism implemented using a very simple technique where there is no for loops. It's entirely tensor operations. So this is much more efficient. Even if you had 96 attention heads, this is not a problem. So now we can have a look at the 12 or 11. So now we can look at the code where we are implementing the multi-head attention with just one class. So this is the multi-head attention class. And in this part, we are just initializing query key value matrices, dropout, etc. But this is the main, this forward function is the main thing. So B is the batch, number of tokens and input dimension. This was, in our example, this was 1, 3, 6. Key is the product of key weight matrix with input. Query is the product of W query with input, and same for values. And then what we are doing is key, query, and value, we are unrolling such that the last dimension, instead of it being 6, it will be the product of number of attention heads and dimensionality of the query key value space per attention head. So the last 2 dimensions will be number of heads, head dimensionality. So that will be key, query, key value, and query. Then what we have to do is we have to take the transpose. So this transpose is taken such that we are grouping not based on tokens, but rather we are grouping the tokens based on heads. This also we discussed. So we are transposing the item at dimension 2 and dimension 3, which will be in Python. The dimension start from 0, 1, 2, 3. So it will be, you are transposing 1, 2. So this also we discussed. And then to compute the attention score, you have to do query multiplied by transpose of key. But this also we discussed here. When we take transpose of key, we are effectively taking the transpose of the last 2 dimensions in the tensor. So last 2 dimensions are dimension 2 and dimension 3 because dimensionality starts from 0. So we take keys.transpose of 2, 3 to calculate the attention score. Then we construct the upper negative infinity masked attention scores, which is this. Then we construct attention weights by taking softmax of the scaled attention scores. What is the scaled attention score? Attention score divided by the square root of dimensionality of the query key value space. Then attention weights, we can, on top of it, we can apply dropout. Here, dropout is a parameter we pass in here. If it is 0, there won't be any dropout. If it is 0.1, 10% of the items will be dropped out. Remaining items will be scaled up by 1 by 1 minus 0.1, which is 1 by 0.9. Which is 1.111. Then context vector is attention weights multiplied by values. But then whatever we get here, we are transposing the dimension number 1 and dimension number 2 so that right after this step, we can combine the last two dimensions because we want to concatenate all the items in each individual, all the items from different heads, right? So then what we do is context vector dot cont. So I don't think we need to really use this function to combine heads, because here we have an even simpler way. We can just do reshaping, which is also simple. Where is the reshape? The last item. Yeah. So context vector dot reshape. So we could do reshaping, but I guess this function is much more efficient than reshaping over here. So we combine the outputs from different heads to get the context vector number 1, context vector number 2, and number 3. In the example we discussed, we had 3 input tokens. In the output, we will have 3 context vectors. The dimensionality of the context vector will be d out, and d out is equal to 6. Now we can simply define an object which is an instance of this class. So first we define the manual torch.manual seed for seeding to the random number generator. Now the inputs are 3 tokens. So this is token number 1, token number 2, token number 3, each being dimension 6. And after defining batches, so here I am defining 2 batches. So inputs comma inputs. So 2 batches, each batch will have 3 vectors of 6 dimensions. So it will be 2 comma 3 comma 6. 2 is the batch size, 3 is the number of tokens per batch, 6 is the dimensions per token. And then here I'm printing the batch shape. So after printing the batch shape, it will look like 2 comma 3 comma 6. But here, if it was just inputs comma, that's it, then batch size will be 1. But let's keep it 2 for the time being. Then batch size comma context length comma d in is simply batch dot shape. So the shape of this batch dot parameter is these 3 numbers. And d out, we are manually defining. The output dimensionality of my context vector should be 6. I don't want to increase or decrease output dimensionality compared to the input dimensionality. Then MHA is the object, which is an instantiation of this class multi-head attention, into which we are passing d in, d out, context length. So context length, I'm not sure where exactly we are defining, but I can say context length equal to inputs dot shape of 0, basically number of rows in my inputs. That is context length. This 0.0 is the probability of dropout, which perhaps I can just say dropout equal to 0.0, and then I can simply pass this here. And I can say number of heads equal to 2, and this number of heads I can pass here. That will be cleaner. So I'm defining bunch of my items here, d out, context length, dropout, etc. And then I'm defining the multi-head attention object. And then context vector is nothing but whatever you get out of multi-head attention when you pass your batch into multi-head attention. Batch is your input. Batch will be the 2-dimensional or 2 batch input. Then if I run this, I can print the context vectors. So final context vectors, I should have finally 6 context vectors because my batch size was 2. Each batch had 3 input vectors of 6 dimensions. So finally also I should have 3 context vectors per batch. Each context vector should have 6 dimensions, and like that I have 2 batches. So this is context vector number 1. This is context vector number 2, context vector number 3 in batch number 1. This is context vector number 1, number 2, and number 3 in batch number 2. I can also print the original batch before calculating all this. So print batch also. So now this should also show me the batch. Yeah. So this is batch number 1, the 3 input vectors. This is batch number 1, the 3 context vectors. This is batch number 2, which is an exact replica of batch number 1, the 3 context vectors. And this is batch number 2, the 3 context vectors. So this is how we implement multi-head attention without using a single for loop. Everything was defined as a tensor, and we eliminated the use of for loop. So now even if the number of attention heads in the multi-head attention is 96, it is not a problem. So thank you so much. I think you have now reached a point where you should feel so comfortable thinking about transformer architecture and thinking about self-attention thinking about masked self-attention, thinking about multi-head attention and implementing multi-head attention from scratch. So I hope this brings a lot of clarity, and moving forward, this will help you a lot in understanding how transformer architecture works for vision related tasks. So you have really reached a milestone at this point in this course, and you should feel so proud. This lecture has been a little bit dense because there are so many numbers that we were juggling. But I recommend you to write down these things, especially the batch size, number of tokens, dimensionality of each token, and number of attention heads, and dimensionality of the query key value space in each attention head. So if you write down these things just once, I think this exercise will be complete for you. So we will see again in the next lecture. I hope you are enjoying this series. I hope you are learning a lot, and see you soon. Take care. Bye.